This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello, yes, I'm in the physiotherapy lecture theatre, level 2. Okay, the recording has just started. It wasn't on before, but it seems to have started now. Thank you. That's all right. Oh yeah, but it had already gone 5 minutes. In fact, the clock on the console is way out of whack, so I just have to make a wild guess at it. It's telling, oh yeah, now it's fixed. Goodness me. How about that? Everything's fixed. Oh, no, that's fine. Thank you. Hello. Nobody else came today? Oh, okay. I was nearly going to leave. I have this on the LMS, but I don't know that we took the time to go through it yet. Does this will catch up? Is this one? Not yet. No. I was going to do that today. All right. So I've got a couple of miscellaneous things to cover over. G'day. Still waiting for the lecturer to lecturer's late. You all right? When should I start? Number 2. How many do we need? How many do we need to make it worthwhile?
I think they are coming. We just finished the lecture report.
So, which one was it?
The trial revision.
This is, yeah, okay. But
So we might have a workshop this week.
hang on a minute. Doesn't Lee take those subjects?
Yes.
Someone else does it. Okay. Right. Have you been able to spend time with that sample, the sample questions? The circuit up top. I'll just run through that a bit more. I didn't intend going through this, but I just thought I'd give the answer. And seeing as there's only 2 of you have arrived for the lecture, I'll discuss it with you. 140 millivolts RMS is what I measured, what I calculated for the output noise. That's what we would call noise at the output. Yeah. And we would get that by modelling the circuit as having an amalgamated noise at the input that I would call E and I over here. We can't really show it on this diagram, but that would be the way I would do it. And then, and typically, almost exclusively, when you put all the noises together, that is the noise voltage from the op-amp, the noise current from the op-amp, and the thermal noise from any resistors. When you lump them all together at the input, you get a value that we call ENI. That's the input referred noise. And we imagine that input referred noise gets amplified to create the noise that we might see at the output. So it's as if there's, I'll redraw it down here. We've got a situation where all those noises that we might start off as just having the voltage noise of the op-amp itself. So there's that noise voltage from the op-amp. And remember that there are noise currents that flow through any resistances that are present. And I suppose I should continue to include that resistor, although I think I showed it as a series resistor when I gave you the question. So this will be slightly different. And remember there were noise currents in all those resistors that we modelled as just currents around there. Well, it turns out that all of those get lumped in with the voltage noise at the op-amp input, plus the effects of the noise current at both inputs flowing through those resistors, and we get an overall thing that we call En sub I, E sub Ni, which is input noise, and that will effectively be amplified by the gain of the op-amp. And that's why sometimes you hear the non-inverting gain of an op-amp stage being referred to as the noise gain. So it's when you accumulate all those noise sources at input and then amplify it, then we end up with an output noise. And as I said, I calculated that way back to be 140 millivolts. Just wondering if anybody, those guys of you who just came in, just wondering if anybody has had an opportunity to work through this and has taken that opportunity at this stage. No one yet?
It's on the LMS.
Pardon?
It's on the LMS.
No, it's not on yet. I've just given you the figure, but I will put it there for you. So I'm asking you if you've had a chance to work through it without the assistance of a work solution yet. You're waiting for the work solution. Okay. Fair enough. I'll just throw this in because we're a little bit altered in my plans for what we do today because of the late arrivals. And thank you for coming, by the way. Good morning. How are you? Gave me time to make sure that I rang IT to get them to start recording the lecture. How's that? Wasn't working when I first came. Anyway, that left me wondering whether I'd just record a lecture to nobody then. Anyway, I realise that you're busy with other things. Do you remember we worked out the gain of this was going to be 40 dBs, was it? Is that right? Yeah? And so we figured out what the signal bandwidth was. That was 100 kHz. And so a conservative estimate of the noise bandwidth was pi on 2 times that signal bandwidth. In other words, 157 kilohertz. Do you remember that? No? We did that, didn't we? Okay, we got that far. All right, here's a quick method for you for a reality check. Yeah? Without going through all the detail of the algebra, I'll just say this much and then we'll get on to other stuff for today. If we realise that there'll be contributions from noise voltage, as we talked about before, plus, and we've got that on this chart, and there's also noise current that's conveyed through the resistors, and it turns out that it's going to be this resistor plus the parallel sum of those two, which works out to be just on 200 ohms or 198 ohms. That's why this one's 99 to match those other two So that'll be probably relatively small. And we also need the thermal noise of those resistors, which is likely to be also relatively small. So let's just have a look at the noise voltage, the voltage noise, and see if we can make some sense of it. If I can just say that if we just imagined that we've got units here of nanovolts per square root of hertz, and for vast proportion there's at least 3 nanovolts, and we've got a bandwidth that is 157 kilohertz. How about I call that 160 kilohertz, just to be very rough? In other words, 16 times 10 to the 4th. So the square root of that would be 400. Yep. So how about we just multiply 3 nanovolts by 400? Does that make sense to you? Because what I'm talking about is this area under here, if it goes all the way out to 157 kilohertz, that area will be what we would measure as noise. Does that make sense? And with these crazy units of nanovolts per square root of hertz, all we need do is to multiply by some square root of hertz, and then we would get the right sort of value. So if we multiply by the square root of 16 times 10 to the 4th, that's 400, then that would give us an idea of the voltage noise that we would see sitting at the input just due to EN. Now we haven't allowed for all this bit up here, but can I say that'll be fairly narrow in width, and we would include it to be, strictly speaking, correct, but we get a good kick-off value for this. Yeah. Good. And I guess that accounts for 120 millivolts of the noise then. Because when we amplify it by 100, that'll be roughly ballpark. The major part of the noise would be due to this voltage noise. Does that make any sense to you at all? This is using rough approximations. All right. But that's not what I came here to talk to you about. I came here to talk to you about interference noise. Yep, and yes, I will put this on LMS for you in gory detail, but we need to cover over some other things first, unless you've got any questions. Yeah.
When we're calculating the area of the voltage noise, we change the unit to multiply by square root hertz.
Yeah.
But the noise is changing with hertz frequency.
Yeah, that's why I've multiplied by that. I'm just saying how about we just look at it as the white noise component here, that bit underneath here, right? We just say forget about that change because that's happening at very low frequencies. So can you see that the width, the bandwidth here is this decade covers over 90 hertz. This one covers over 900 hertz. This covers over 9 kilohertz. And that product over, say, this decade in particular, way up to 157, is going to have a lot of energy compared to down here, and certainly therefore down here. So my question is, how much do we need to worry about this lot here? That will come out in the actual calculation.
My point is how we change the unit of voltage noise.
Yeah.
Times square root of Fn.
Sorry?
Yeah, why we time this value?
What? Why did this one here?
Yeah.
That part, okay.
One noise also changes with frequency.
This is the idea, the concept of a noise integral, which is to say, even past the signal bandwidth here, any noise is still going to get amplified progressively by less and 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 less with frequency. So the thought experiment here is to say, okay, we'll have a lot of stuff coming through and that'll be amplified. But if we had a simple brick wall filter, one that approximated that noise that's being amplified at high frequencies, if we imagined a shift of the signal frequency to some arbitrary frequency where this area here was equal to that area there, what would the point be? Yeah? So we can regard it as a block, and that's what I've done here. I've regarded that as a block, just to give me a rough guide to start off with. Yep. These are subtle points, and the area is quite tricky. It takes a different mindset to, but I think you understand that. Any other good questions before I push on? I'll try and elaborate that when I put the solution up on LMS. But thank you for the questions. Okay, moving on then. This is on LMS from a few weeks back, and I didn't get to it at the time. Did I? I don't think I did. Okay, this is, we've talked about noise in devices. This is the noise inside your system. Now I want to talk about the noise from outside. That's the interference that we've experienced many times, and also to discuss a little bit about shielding and guarding. So basically 4 mechanisms for interference, coupling interference into circuits of electrical nature, and we've got some ways of dealing with them, and there's also the method of signal guarding as a form of shielding, and I want to talk about that in terms of right leg drive. Now, a couple of here's listed the interference mechanisms: conductive, capacitive, inductive, and electromagnetic. So first up, we've got this idea of a resistive coupling through a ground loop, and that is to say, when there are 2 earths, and it might have been better if I'd used the different symbol for a ground for one of these to show that it's not exactly the same ground. And the idea is that, supposing in this room we've got 2 power points, mains points right on opposite sides. So ostensibly the grounds of those 2, the green wire or the green-yellow wire, are connected together, but in so doing there is some distance between the 2, so there will be some finite, albeit very small, resistance between those 2 grounds. Inadvertently, we might have a tram going past out in Royal Parade that creates some ground current in its powering, something like that, and it just happens to drag current through between those 2 points. Through that finite but very small resistance, if there's a large current through that, that will produce a voltage. Yeah, and that voltage is shown here as VCM. It's between two different points that are supposed to be ground, and sure, they're connected together, but doesn't matter if there's a big current flowing through whatever tiny resistance, there will be a voltage. That voltage will then appear as a common mode voltage between this point and that point, and thereby possibly get amplified in the amplifier. So given that it might be a mains current down here, then an alternating voltage, then we might get something that's still small, but if we've got a high level amplifier in a sensor system, that can be a problem for us. And how do we get around that? Well, we try and make these grounds as electrically short with each other as possible, and the resistance as small as possible between the two. So we talk about single point grounding, and try and minimise the number of grounds as well, so we don't have the opportunity for that cropping up. The next one is what we're kind of used to, and now I'm looking at this, it's from a Dutch book from antiquity. Did I ever mention this as a voltage source symbol to you? Did I get around to that? It's kind of an intelligent symbol for an ideal voltage source, because you can see it's got a short circuit running through it. The converse version for an ideal current source in this European style is when it comes around, just that. So that looks like an open circuit for an ideal current source. So that one, for a real current source, would have a shunt around it, and the ideal voltage source, as we've seen there, would have series resistance associated with it. So this would be a V and this would be an I. Okay, so that's just a fairly smart symbol that seems to be in use in Europe quite a bit. Didn't really catch on too much here. Did I also mention to you that for current sources we often see a double bubble thingy? That's also originated in Europe, but seems to be in USA literature as well, just as an aside. Okay, coming back to it then. So capacitively coupled through whatever insulator there is here, and typically a mains wiring couples into a circuit. And I think you've seen the value of that. Probably some students in the workshops, I've got them to hold on to an oscilloscope lead just to see that the main signal comes in, and that can be 20 volts or so, which is sort of between this capacitive impedance down to ground through whatever value goes through the capacitor or through your boots down to ground. Now, obviously the capacitance will decrease if we increase the distance away of this, because we're separating the notional plates of the capacitor. Now, we imagine this coupling to be of a capacitor, dielectric being air, principally, and capacitance is, inversely proportional to plate separation. So if we separate the notional plates, then the capacitive coupling becomes less, and we get less interference put in. What else do we do? Well, we can use some screening, and we've talked a little bit about that. We can screen this wire with a sacrificial shield that goes directly to ground. Now, the tricky bit is here that that shield is better if it's connected to ground at the low impedance end. And damn it, as chance would have it, usually for a voltage driven, well, obviously we have sensors that are typically voltage driven. So the low impedance end is at the sending end, which is the least accessible for us to connect to ground, usually, unfortunately. So if we connect the shield to ground at this end, it's got a pathway that's not as good at passing that signal directly to ground as it will be at the input. But if it's a current at this end, then the opposite applies, and yes, it's good to ground at the measurement end. Okay. The ways that we do it, of course, is the coaxial cable, the shield around the outside of the connector, or a twisted pair. The signal lines are twisted around each other. That means that from both the cables, both the wires experience the same amount of interference induced in them. So if we then take our signal and use a differential amplifier on it, as you well know, we cancel out the interference and preferentially pass the signal as a differential signal. All right, and here we are again with capacitively coupled signal coming into a typical circuit, and with the shield, the capacitive coupling is bypassed directly to ground via this low impedance grounding shield. You've seen these shields, they're kind of a mesh of wire that encapsulates the signal lines, and if we're lucky, the signal lines are not separate and we don't use the coax cable as a return path, but we can do that. You have to be careful with grounding, because suppose you put a shield in and you don't use it properly, then you've got a piece of wire ready to accept interference, and it will act as an antenna then. Picks up the interference and passes it into the signal lines if you don't have it grounded. If there's no pathway here, from here to connect to ground, so you'd want a wire or some capacitor or something to connect between those 2 points. Otherwise, it's just a collector for interference to re-radiate into the signal lines. So, think about it. It has to be done, otherwise it's not worth the effort in the first place. Oh, here's a good one. The typical interference signal still experiences capacitance internally of some level, and tiny capacitance between the shield and the signal lines in the cable. So, what do we do about that? Well, if it's a digital line, then we can use alternate earths between signal lines. That happens a fair bit. Notice here that the signal lines are constrained inside ground points. The other one is to use the twisted pair as well as the shield. So back here, you can typically these are combined. Twisted pair inside a shield. Now this bit here, I saw this in an app note and I thought, hey, what's this about? Well, it turns out that it's an excellent twisted pair of pairs. The reason why I bring it up is that one of my colleagues working in EEG had a difficult situation where he was using the system in a very high magnetic field. It wasn't magnetic resonance, but magnetic stimulation, TMS. And it turned out that they couldn't figure out how to do the interference with normal cable, but they had typical single cables that were specifically organised for TMS applications. So I suggested that they try this, and it turned out that some of the people in the department were good at knitting, and one of the office staff was excellent at braiding these things. You can buy this from the States, but it's very expensive. It turns out it's got very, very good noise rejection just through the geometry. I haven't actually gone through it to figure out why particularly, but I just report it as being something that's very useful for that particular application. So it's a kind of a loom arrangement, and I can't remember even what they call it now, but it's available at that website. Right. Guarding. Sometimes shielding is called guarding, and sure, it does guard because it's guarding the signal line from involvement externally, but we also have the idea of an active guard, a driven guard, where some proportion of output signal, common mode output signal, is pushed back onto the shield. And the idea behind that is that if you've got 2 points at the same voltage, then no current will flow between them, right? 2 points at the same voltage, same potential, there won't be a current flow, no matter what the impedance is between them. So if there's a common mode signal that we want to guard against, if we can somehow put that back onto the shield, then we neutralise that particular aspect of the signal. And here it is in terms of our familiar 3 op-amp instrumentation amplifier, where common mode signal is picked up between those 2 points as an average of op-amp output 1 and op-amp output 2, and it's actually sent back onto the shield. It turns out that even though this diagram, the previous diagram, is not very detailed, a bit notional, it highlights the fact that it's sometimes, well, it's invariably useful to reduce the amount of signal that goes back, not exactly as shown here, a complete value of VCM being pushed back on the shield, but a lesser proportion of it, a fraction of VCM, maybe a large fraction, but not the complete amount. And the reason for that is that we can get instability occurring with these systems. Just while I'm on it, where else could we get VCM in that circuit? Ask your colleague beside you where you think VCM would be apart from in this spot. If we didn't have 2 20K resistors, how would we get VCM fairly easily in this circuit? Sorry, where?
Wouldn't take it from RG,
RG.
no.
Yes. In a way. But you have to adapt RG to do it. How would you do that?
Have to split this. I know RG acts as a, I don't know if it's a complicated word for it, but it's a very special resistor instrumentation amplifier. So would you have to
That's good. Yeah. The sub G stands for gain, by the way.
it's gain.
Gain setting. Yep. 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 Yep.
I don't know how to use it in this context.
Remember, I might have mentioned to you a good way to analyse this circuit is to do it separately for common mode and differential mode. Like if V1 and V2 are equal, then the voltage here is going to be V2 equals to VC. We'll say V1 equals to V2 equals to VC. This voltage here is equal to V2, so that'll be VC. So this will be VC here. This voltage is VC, so that one will be VC because we've got negative feedback. So that point will be VC as well. So from a common mode point of view, there's no current flowing through RG. Good, okay. So that means that this is VC, whoops, dang it, oh dear. This point is VC also, and so is that one. So we've got a gain of 1 for common mode signals, remember? How did we analyse for diff mode? If this is half of a differential voltage, and this is minus half of a differential voltage, then we've got minus half here and plus half here, so there's a definite voltage across that resistor inspiring a current flowing upwards, and so there'll be an amplified version of V1 on 2 here and minus V2 on 2 down here. Pardon?
Does that depend on what RG is?
Well, it will, yeah. It'll be an amplified version. But we think of these two as independent. We can think of these two op amps as being independent, non-inverting amplifiers. And the gain would be set by, for the first one, R3 divided by RG on 2, right? Why RG on 2? Well, the midpoint here is virtual ground. So we have a gain of R3 on RG on 2 plus 1, and likewise for this one. Okay, so if we're going to all that trouble, we might as well pick off our common mode signal at the midpoint there, because that's where a common mode signal will be. Yep. Good. So we don't need these two resistors. We can just split this one and take common mode signal out from there, providing we don't create more noise in the process. Yes? Sound good? Questions? No? Okay. All right, so with common mode signal on that shield, we would get repel any common mode interference signal that might come in, as well as this one that's shown directly coming in at the input. There could be interferences. Well, we're modelling that external interference as that common mode signal there. Gripes, time flies. Okay, what's the big deal about common mode signals? Well, shown here, with these cables that have got differential connections, and maybe we've got them hooked up to electrodes that I want to talk to you about in the very near future. The electrodes they might have two electrodes, one right arm, one left arm, and they might come unstuck separately, so the resistance could increase. They might age, resistance increase. So I don't know whether it's apparent, but for any common mode signal, if it's being applied equally to both electrodes, and maybe the electrodes have aged a bit and become more resistive, or they've broken off. If there's a problem with the internal resistance of the electrode, connected to the skin, whatever, or there's a problem with the capacitance, which might be from a similar point, or both, then we might get V1 and V2 as no longer being equal from an equal proportion of common mode interfering signal. Yep. So suddenly, common mode signal has become differential. It's different at both points. Therefore, our snazzy instrumentation amplifier will amplify that as if it's a differential signal. Yep. Common mode gone differential, gone feral. So that's something to watch out for. Heavens, we're running out of time. Here's where the alternative to the guard circuit is presented, and we actually have the common mode signal now derived from the same place as before, and once again we could have taken it from a tapping point halfway through the gain setting resistor. That now is being inverted and a little bit of capacitance put in. It's got an integration function here and some resistance to protect the subject, but we've got the common mode signal being put back into the right leg. So next time it comes around along with right arm and left arm signal, it's been subtracted away from itself, if you will. So we've reduced common mode signal by stuffing it back into the patient's leg. Yeah. As you'll appreciate, with that cyclic behaviour, knowing as we do know about instability, when we've got systems with some gain and there's a phase shift and inversion, then what might have been subtraction away ends up being addition. Yes, sir.
So, in the original diagram of the instrumentation amplifier, when the VRF is kept instead of the ground.
We're referring to this one?
No.
No.
The actual one.
This one here?
The one that is studied in biosystems design. In that, the instrumentation amplifier was in place of VRF. The VRF was instead of the ground.
Oh, yeah. Yeah, okay.
So, like, why couldn't this be used in a situation like that? Is it like because of the sensitivity, or is it for some other reason?
Oh, the VREF.
Yeah.
There's another aspect of electrodes that's an offset voltage. Yeah? The electrodes themselves act like little batteries. With the silver chloride ones that you were using, it's about 0.3 volts. And that can get amplified by these things that, as well as being AC amplifiers, signal amplifiers, they will also amplify a DC. Yeah? And that might be, the VREF here, might be there to compensate, to put effectively minus 0.3 or whatever is required once it's gone through the cycle to do that. I actually haven't, I'm not sure what the author's meaning was there yet. I'll check up. Yeah, I'll report back this afternoon on that. Thanks for the question. But can you see that this is sort of opposite in a way? We've got a unity gain non-inverting buffer here. And here we've got an inverting amplifier. So this is putting a opposite polarity signal out to be subtracted away from common mode signal here. In this case, common mode signal is being placed on the shield so that it will reduce the amount of interference signal that's induced into the signal cables, because once again, if you've got 2 points at the same voltage, then no current will flow between them. So it intercepts interfering signals that way. I think we're running out of time here, but I'll just talk about magnetic coupling, and that's where you've got a magnetic field cutting through a sizable loop. And the magnetic field here is shown as the X's. They're the flux lines going through a magnetic loop, so that we could get a voltage induced as a result of that. And once again, the solution is to use the twisted pair to reducing the area of the loop first up, or this orientation of the conductor. We might switch, if you can use your imagination here to say, let's switch that into the horizontal plane. So both wires are on the same plane, both these two wires, this upper one and lower one, we'll flip them through 90 degrees so that they are transverse to the plane, and that way there's no intersection of a field across the loop anymore. So that will minimise the induced magnetic field. We can use forms of shielding with copper or mu metal. Now the method of shielding in this case is to ground at both ends for a subtle reason, and I remember I said it's better for capacitive coupling to ground at the low impedance end. So that's the voltage end, the sending end if it's a voltage that's being sent, or the receiving end if it's a current that's being sent. You can ground at both ends, but the problem then is that we have that same problem of the conductive coupling where earth loops can persist as a result. Okay, the last one is electromagnetic coupling of travelling waves, and that's specifically a problem if we've got holes and seams and things, and you'll note that sometimes you might have encountered chassis that have a lid that's got a gasket underneath it. So that conductive gasket is meant to reduce the seams, the apparent seam, so that we actually want to make the dimensions of any holes that would allow magnetic coupling in to be less than 1/20th of the wavelength of that interference. Also, screws are put into lids and things like that at specific distances, and they're usually, set up to be less than 1/20th of the wavelength for that reason again. And the vulnerable accesses are things like ventilator holes and switch holes and panel holes and deconnector holes and things like that. So it might seem like often not much attention's been made for it, but we usually make such holes or gaps as being very narrow. I'm looking for an example, but I can't find one. No, nothing's apparent here at the moment in any of the equipment that we can see nearby. Yeah, well, there's a fair degree of literature on the materials that are used. As I said before, steel, copper and mu metal are the ones that are of good use. Okay, so interference is conductive, capacitive, inductive or radiative, and we can use different forms of shielding for that. Signal guarding is widely used to convey off common mode interference, and also right leg drive is used in ECG systems as another form of cancellation of common mode signals. Do we have any questions at all? I've gone over time, 12:01. Sorry about that. So, do we meet this afternoon? Yes? How late should I be for that?